Hello, in this video we're going to be looking at another integration technique. This one is called integration by parts. Now if integration by substitution is the opposite of the chain rule, then integration by parts is the opposite of the product rule. And you can see the product rule there at the top of the derivation. So if we rearrange it and integrate it, we can find this new rule called integration by parts. So if we make u dv by dx the subject and integrate it, we get a middle term of the integral of d by dx of uv with respect to x. So that's basically differentiating and integrating something. So we end up just with uv. So our formula at the bottom, the integral of u dv by dx with respect to x is equal to uv minus the integral of v du by dx with respect to x. So this formula is called integration by parts. And as I've already mentioned, we use it to integrate products. Okay, so our product is going to be made up of u and dv by dx. And unlike the product rule, where it doesn't matter which is u and which is v, we will have to decide which part to set as u and which part to set as dv by dx. But we're going to be differentiating u to get du by dx, and we're going to be integrating dv by dx to get v. So I'm going to be talking you through how we make those decisions. And just like the product rule, I rewrite it in a simpler form as far as I'm concerned, which is the integral of uv dash equals uv minus the integral of vu dash. Now, no pun intended, but I've split up the integration by parts into 5 parts. And in part 1, we're going to be integrating x multiplied by a function of x. Now, I haven't mentioned this yet, but as the formula shows you, whatever we choose for u and v dash to integrate, it equals uv minus the integral of vu dash. So we want vu dash to be easier to integrate than what we're starting with. So in this example, the integral of x sine x dx, if we were to use v dash as x, then that would integrate to give us half x squared, and that is not going to be any simpler because we're still going to be multiplying it by sine or cos. So if we let u equal x, then u dash equals 1. That is definitely simpler. V dash is sine x, gives us v equals minus cos x, and it really didn't matter whether we integrated or differentiated sine x because it was going to be a multiple of cos x anyway. So substituting into the formula, uv is minus x cos x. The formula then has a minus sign, and then the integral of u dash times v, which is minus cos x times 1, i.e. minus cos x. So we've got minus x cos x minus the integral of minus cos x dx. The two minuses can turn into a plus, so it's the minus x cos x plus the integral of cos x dx, and the integral of cos x is sine x. So the final answer is minus x cos x plus sine x plus c. And now we can apply the same idea to x times another function. This time it's the square root of x minus 3. So again, if I use v dash as x, I'm going to get half x squared, which is going to be more complicated than what I want. But if u equals x, then u dash equals 1, and if v dash equals x minus 3 to the power half, then using integration by substitution, v will be 2/3 of x minus 3 to the power of 3 over 2. Substituting into the formula, uv is x times 2/3 of x minus 3 to the power of 3 over 2, which we would normally write with the fraction at the front, the 2/3, then the x on its own, and then the x minus 3 to the power 3 over 2. Minus sign in the formula, and then the integral of vu dash, that's going to be 1 times 2/3 x minus 3 to the power 3 over 2. I've put the 2/3 out the front as a constant, so we still need to integrate x minus 3 to the power of 3 over 2. Again, we would use integration by substitution for that, so we would add 1 to the index, i.e. 5 over 2, we would divide by that index, i.e. times by 2/5, and that's why we get 4/15, because that's 2/3 times 2/5. So the answer is 2/3 x minus 3 to the power 3 over 2, minus 4/15 of x minus 3 to the power 5 over 2, plus c. So let's apply this formula to the integral of x squared e to the 3x. Again, that's a product. Again, if I put v dash as x squared, I'm going to get a third x cubed, which is making things more complicated. Whereas it doesn't matter whether we differentiate or integrate e, we're still going to get some multiple of e to the 3x. So if we let u equal x squared, then u dash is 2x. That is simpler. because it's a lower power. V dash equals e to the 3x, and by integration by substitution we get that v is a third of e to the 3x. Again, substituting into the formula, we have uv, which is 1/3 of x squared e to the 3x, minus from the formula, u dash times v is 2x times a third e to the 3x, which is 2/3 x e to the 3x. Again, I can put the 2/3 out the front of the integral as a constant, so I want to integrate x e to the 3x with respect to x. Unfortunately, the only way I can integrate x e to the 3x is to use integration by parts, i.e. I'm going to apply the same formula again. So this time, this is like part 1. We have u as x and u dash as 1, v dash as e to the 3x and v as a third e to the 3x. Then bearing in mind that we've already started this question, we get a third x squared e to the 3x from before minus the 2/3, and then in the square brackets, this is where I'm applying the formula again. So our new uv is 1/3 x e to the 3x minus from the formula a third e to the 3x. I put the third out the front as a constant. So we need to integrate e to the 3x dx, which we can do. The integral of e to the 3x is a third e to the 3x. So on the next line, again, we've got our first term of 1/3 x squared e to the 3x. We don't have to integrate the next bit, so I've just done 2/3 times a third, which is 2/9. So we've got minus 2/9 x e to the 3x. And then again, 2/3 times a third is 2/9, but we've got two minuses making a plus. So 2/9 of the integral of e to the 3x dx. And since the integral of e to the 3x is 1/3 e to the 3x, we get 2/9 times a third, which is 2/27 e to the 3x plus c. Now notice that we had x squared e to the 3x and we applied the formula twice. If it had been x cubed e to the 3x or 4x or whatever, then we would apply the formula 3 times, because each time we're going to differentiate our, say, u equals x cubed to get an x squared term, then an x squared term to get an x term, then an x term to get a number. So whatever the index of x is in examples like this is the number of times we would have to apply the formula. So in both parts 1 and 2, we had x or x squared times the function of x. And in both cases, we started with u equals the polynomial of x and v as the function of x. Well, here is an example where that is not going to apply. So we've got the integral of x to the 4 ln x dx. And the problem is I can't integrate ln x. So I can't put v dash as ln x because I don't know what the integral is. So regardless of whether I know if it's going to work or not, I'm going to put u equals ln x and u dash equals 1/x. And I can have v dash as x to the 4, which gives me v equals 1/5 x to the 5, which in all other examples I've said is more complicated, but let's see what happens. So using the formula, uv is ln x times 1/5 x to the 5, and then our vu dash is 1/x times 1/5 x to the 5, and all that happens, because we've got 1/x as u dash, is that we end up with a 1/5 of x to the 4. So I put the 1/5 outside and the x to the 4 in the integral sign. The integral of x to the 4 is 1/5 x to the 5, and 1/5 times 1/5 x to the 5 is 1/25 x to the 5. So in this example, where we have a power of x and log of x, then we don't put the x to the n as our u. We put it as our v dash, and we put ln x as u, because when we differentiate ln x, we just get 1/x. So all we're doing is reducing the index of the x polynomial by 1, and we can still integrate it. Okay, so in part 4, we're going to look at how to integrate arcsine x dx, which has only got one part, so I'm going to write the number 1 in front of it. So we've got the integral of 1 arcsine x dx. Now I've got the same problem as I had in part 3, but if I write v dash as arcsine x, I'd need to integrate it, and I don't know what the integral of arcsine x is. It's the whole point of the question. So I'm going to write u equals arcsine x, and as we saw when we were doing the inverse trig differentials, u dash is therefore going to be 1 over the square root of 1 minus x squared. Also, we're going to have v dash as 1, which means that v equals x. So applying the formula, uv is x arcsine x, and from that we're going to take away the integral of u dash v, which is x over the square root of 1 minus x squared dx. So then the question becomes, how do we integrate that? Is that any simpler than what we started with? Well, here we can use a substitution. So if we let u equal 1 minus x squared, then du by dx is minus 2x, and dx is du over minus 2x. And you may notice that the x on the top, the numerator, is going to cancel with this x on the denominator of our dx substitution. So that gives us x over u to the half multiplied by du over minus 2x. The x's cancel out, and that gives us minus a half, which I've put outside as a constant, multiplied by the integral of u to the minus a half du. Integrating u to the minus half gives us 2u to the half, and then when we times that by minus half, we just get minus u to the half, which, going back to our x, is minus the square root of 1 minus x squared. And hence the answer to the question is x arc sine x, that's uv, plus, because the formula has a minus, but we've got a minus in our integral, of plus the square root of 1 minus x squared plus c. And finally, part 5, what I would consider my favourite part of integration by parts. And here we've been asked to integrate e to the x sine x with respect to x. So as always, we have to decide which one's going to be u and which one's going to be v dash. Now it doesn't make any difference as long as we're consistent. So in this case, I've chosen u to be e to the x and v dash to be sine x, from which u dash equals e to the x and v equals the negative of cos x. And then we substitute those into the formula. So uv is negative e to the x cos x, then we've got a minus sign, and then vu dash is also e to the x times minus cos x. So those two minuses can become a plus. So we get minus e to the x cos x plus the integral of e to the x cos x dx. So we can't integrate that without integrating by parts. So we're going to let u equal e to the x again. V dash this time is cos x, u dash is e to the x, and v is sine x. And then remembering what we did before, we've got minus e to the x cos x plus, now we're using the formula, uv is e to the x sine x, minus from the formula the integral of vu dash, which is also e to the x sine x dx. And it looks like we haven't really made any progress because we've just got back to where we started from. And that's why I've written I equals at the beginning, because we've regenerated the same thing. So I can write I equals minus e to the x cos x plus e to the x sine x minus I, where I is the thing we want to find. So if I add an I to both sides, I get 2i is equal to e to the x sine x minus e to the x cos x. And then if I divide by 2, I get I, the answer to the question, is equal to a half, open brackets, e to the x sine x minus e to the x cos x. And if I wanted to, I could factorize out the e to the x as well.